Welcome to today's webinar. My name is Andy Fay, and I'm a Product Marketing Manager here at DeMathWorks. Today we're here to talk about thermal analysis with FLIR cameras in MATLAB. Today, however, I'm joined by a very special guest of mine. Dave, would you like to introduce yourself?
Thank you, Andy. Yes, my name is Dave Purcell, and I'm the VP of Worldwide Sales at FLIR Systems for our R&D Science Solutions group.
So just to kind of give you a preview of what we'll be talking about for the next 30 minutes or so. First, we'll give you an overview about thermal imagery. Dave will do this and talk about some typical applications. He'll talk a bit more about how to initially work with thermal images. And then I'll take over and talk a bit about how MATLAB can help extend the capabilities of these cameras. And with that, we have several demonstrations that I think will resonate with you all. And then finally, we'll have a summary and just kind of a preview. We have a little bit of a surprise for you at the very end, kind of showing off some of the collaboration FLIR and MathWorks have been up to. So let's start on our first topic. So Dave, why don't you get us kicked off and give us kind of an overview of FLIR and the kind of technologies you have?
Sure, you bet. What we do at FLIR Systems is we engineer, manufacture, market, and distribute technologies that enhance perception and awareness. And we do this through various technologies where most people know us for our thermal imaging systems, but we're also involved with the visible light imaging systems, locator systems, and also threat detection systems. And how we go to market with these technologies is through these segments. We have 6 segments at FLIR Systems that are displayed here on this slide. They include surveillance, instruments, OEM and emerging technologies, maritime, security, and detection. The group that I work for our R&D Science Solutions is found underneath the Instruments section. I would say most people are probably familiar with FLIR from our Surveillance segment. But most recently, we released some new technologies in the OEM and emerging marketplace to include an infrared camera or thermal imaging camera that works with the iPhone 5S. It's called our FLIR One. We're pretty excited about that, and that's out of our OEM and emerging technologies group. Now, Andy, when most people, like I said previously, think of thermal imaging, they think of finding bad guys. And that's part of our surveillance group. Most recently, we had an event here in our neck of the woods in the Boston area. An unfortunate mishap at the Boston Marathon. There was a bombing, and then we had some suspects on the loose, and the local authorities here in Boston actually utilized our technology, a FLIR camera mounted to a helicopter, to find one of the suspects. And they did so by identifying his heat signature underneath a plastic cover in a boat. And those images are shown here. And I would say, yes, when people hear the term thermal imaging or infrared, they think finding bad guys. But in reality, thermal imaging can do so much more. It can produce more than just a thermal image or locate a bad person. Some of these technologies can be calibrated to provide measurement. Specifically, we can make temperature or radiometric measurements with certain calibrated instruments. And this is an example here, Andy, of a printed circuit board, and overlaid on top of this visible image is a thermal image of that printed circuit board. And just by looking at the board, when you realize that the lighter colors, the whites, the yellows, represent warmer temperatures, and then the blues and the purples and the blacks represent cooler temperatures, you can look at this target and very intuitively do a qualitative analysis and say, I can see areas on this target that are warmer than others.
Exactly. The areas that were totally invisible in the visible spectrum. It's just so intuitive to see it from this perspective.
What most people don't realize is that with a calibrated camera, I can extract now temperature values, or as I mentioned, radiance values from that image. And I've drawn a grid work on top of this thermal image that represents the individual pixels or the individual detectors where I can extract temperature information. That's where it really starts to get exciting.
Yeah, so it's essentially like having, looks like thousands here of little thermocouples, right, at each pixel level. But
that's exactly right.
Yeah, but whenever you introduce, thermocouple, just by connecting it actually changes the thermal characteristics. So this is totally non-intrusive without even affecting the actual material itself.
No, that's an excellent point, Andy. This is a non-contact measurement methodology. which, as you mentioned, in some instances, especially with printed circuit boards, when the targets are very small, if you apply a thermocouple to that target, you could actually change the thermal characteristics or properties. The thermocouple, in a sense, becomes a heat sink, which is what it's designed to do.
Yeah.
And as you mentioned, it's like having several thousands spot radiometers or thermocouples when you have this calibrated thermal image. In fact, this particular image is made up of 640 by 512 pixels, which is over 300,000 individual measurements.
Wow.
So it's quite powerful.
So tell me, Dave, how does one get started? So you have one of your cameras. I'm curious, how does someone actually start doing some thermal analysis?
Oh, that's a great question. There's primarily two ways to do the thermal analysis with the cameras. One way is to do it right on the camera itself. We have some camera systems that almost look like camcorders. And they behave very similarly, except inside of the camera there's a thermal sensor versus a visible CCD. So with these camcorder-style infrared cameras, we can capture still images, we can capture movie files, and we can do thermal analysis directly on the camera. We can apply spot tools or area tools and extract temperature information right on the camera. The other way is to take the information from the camera and stream it to our software called Research IR, and it allows us to do more in-depth analysis on the thermal information than we could do on the camera itself. So for example, in the Research IR software, I can connect to a camera, I can control the camera, I can adjust focus, I could adjust the level and span parameters or contrast and brightness on the camera. But once I have that imagery now in the software, I could use additional analysis tools, spot tools, area tools, polygon tools, freeform tools, segmentation tools. I mean, the list goes on. But essentially using these tools, I can extract that temperature information. And then I can display it in plots, like temporal plots, time versus temperature temporal plots, in graphs like line profile graphs, histograms. In the software, I can also do mathematical functions for those spot and area tools. So I could do subtraction, multiplication, or more advanced type functions per region of interest or per analysis tool. And then I can spit all this out and share it with other people as well. But our software is really built to be something that's off the shelf, plug the camera directly into it, and I can be running in minutes and doing thermal analysis both qualitatively and quantitatively.
Wow, that's great. So yeah, it seems like you really help people, like you said, get out of the box very quickly and be very productive. And it sounds like you do some very good basic image processing, right, to kind of highlight areas and maybe create reports and trying to do diagnostics.
We do, and we really try to cover or capture the majority of testing that needs to be done. But I'll be honest with you, Andy, there are situations where we have customers who want to go beyond just what we do in our Research IR software. And some of the things they may want to do include doing functions based upon a matrix level, not just on a spot or not just on a region of interest, but they want to do it for the entire image. And sometimes those analytics or that functionality can include doing things like target tracking, or even real-time fusing of multiple sensor technologies. Like it could be thermal, it could be visible, it could be multiple thermal cameras operating in different wave bands or spectrums. Those are some of the things that we get questions on when we're working with customers. What could I do beyond this? And it can get quite advanced.
Great. All right. Well, thanks so much for the intro. I guess now it's my turn. We'll get into a little bit of MathWorks here and how we can help the situation. Let's start out with a typical image and video processing workflow. For those of you who are familiar with MathWorks already in MATLAB, this will be familiar. For those of you who are new, I'll walk you through this and really show you that it's going to be very similar. There's only going to be a slight change when we actually start working with FLIR software as well as their hardware. So first of all, the first part of our workflow is we're going to need to access hardware, software, maybe actually files. Then we're going to go into exploration and discovery. So once you get your data, you're going to want to try to look at it, run maybe different types of functions, filters, really try to find, in our case, maybe there's certain thermal characteristics we're trying to extract, see if certain things are happening over time. So with this, you can do this in the discovery and exploration stage. And once you kind of figure out kind of what algorithms need to be applied, maybe what the answer is, you then start to share it with others, right? So this can come in the form of actual maybe video output, images that have highlighted areas. It could be actually output, for example, C code and other types of files that now need to be consumed with other types of products. And I should point out too that this is actually a very iterative process. So rarely is it a single pass through. You're normally going to go through this and you're going to go back to access and collect more data, really refine your algorithms, and then you're going to share, get feedback from the people you're sharing with. And so this is really the technical computing workflow, and why MATLAB lends itself very well to this type of workflows, because it's a very interactive environment. Now, if we move to thermal imaging, really the only subtle changes, if you see in the access area, is that we're working with real hardware, real thermal cameras from FLIR, and we'll talk about how we connect to some of those in a minute. We're actually working with their software. So kind of, what I mentioned earlier, we have a surprise. So we have a way, we'll show you later, of how we connect more intimately with their research IR software and to exchange data back and forth. And then finally, if you had cameras, for example, that are saving files, these temperature files, we can import those in directly as well. So we're going to, again, go through this workflow and use this exact workflow through the next couple demos.
So Andy, just to be clear, make sure that those participating in our webinar understand, you can take a FLIR camera and import right from the camera into MATLAB today.
Absolutely.
Wow.
So yeah, our image acquisition toolbox has been out for a very long time and provides many of the common standards. And that's great that you actually adhere to the standards related around vision. So Dave, coming back to, you said some of the ways that maybe MATLAB can help to extend the capabilities of a camera. You mentioned like fusing sensors. So actually, here's our first example. If you see our image here, my current setup, I actually have one of your cameras here. This is one of your test bench setups. I think it's a FLIR
It's an A35SC benchtop test kit.
Great.
Yeah.
And you can see I'm connected actually through gigabit Ethernet, Gigi Vision, and I'm using a webcam below. So essentially I have two sensors here. I have a thermal one and a visible one. And as you can see, if I draw these lines here, they have different focal axes. So they're off alignment. So if I were to just post these images on top of one another, they would, one, not align. And you'll see that here in this image. And then also, there'd be different scales. They'd be essentially not very useful. And so what I'm about to show you is how to actually do sensor fusion. So just to kind of show you what the end goal is, here you see I'm actually running in MATLAB. Here we've done sensor fusion. So essentially we've fused together and warped the visible image right onto the thermal image. And you can see the little lights blinking there as well.
Yeah, so this is great because now I can see thermal cycling happening on the board, but I'm seeing it in the visible spectrum.
Exactly. And if you were just to see it in the visible spectrum, you definitely lose a lot of context.
Yeah.
So this is very powerful, and this is really how sensor fusion is really great. Is you can pick different spectrums, different type of sensor types, and fuse them to give you a more comprehensive type of image.
Now, Andy, you were just changing the position of the cameras respective to the target, and I noticed that they stayed aligned. So you can do this on moving targets.
Absolutely. So yeah, you can definitely. You see, I'm running on my PC, and pretty much we're able to scale and move with both images being fused consistently. So this really, again, gives you a very nice canvas for how you can look at it and get just a lot more detail.
That's excellent.
So let me show you now in MATLAB how we actually did this. Okay, here we are in MATLAB. For those of you who are new to the environment, I will go over some of the features as I go through them throughout the demonstration. So here we are. We have actually two cameras, like we said, connected to the computer. We have the FLIR camera as well as a webcam. So how do we connect to the FLIR cam? So we're actually going to use this thing called GigiCam. And so this is actually a function. If I hit F1, you'll see I get the help here. So essentially this is going to connect through the GigiVision interface. And to get the correct IP address, and you can see you can connect to the camera using the IP address, this device number, or the serial number, you're going to type at the command line, and you can type GigiCam list, and essentially it's going to go out and query, and you can see it found the FLIR camera, and here's the IP address of the camera. So I've already entered that in, as you see up here above, and what we're simply going to do is grab a snapshot of it, and we're just going to stretch out the contrast so that I can see it over a larger range. So let's go ahead and run this section. And you'll see here I have these little double % signs. Essentially, MATLAB allows you to run these little sections of code so you can actually bounce around and run out of order without having to recompile anything. So that's one thing that's really nice about MATLAB, is that it's a scripting language, and you can essentially iterate on different variables very quickly. So going back to my image here, you can see that I have captured a snapshot of from my FLIR camera. Now I'm going to acquire a snapshot from my webcam, and here I'm creating a webcam object. Let's go ahead and run that and get a preview. And as you can see, I have my webcam and I have my thermal image. And like I said before, these are very different, right? We not only have different field of views, the webcam is capturing a lot more as far as of the tabletop. The scale looks different as well. You see the FLIR camera, the image is larger. So you can't just overlay these, right? You saw it earlier. You need to do what's called sensor fusion, or really in image processing terms, it's called image registration. And so we're going to essentially align these two images together. And the way you do that is simply a technique, and the technique we're going to use is called control point registration. And so here is the actual function I'm going to be using, CP select. So if I hit F1, you'll see the help here, control point selection. So essentially this is going to bring up a tool that I'm going to map points from one image to the respective same location in the secondary image. You'll see that in a second. And essentially the concept is you have a moving image and a fixed image, and you're going to essentially warp the moving image onto the fixed one. In our case, our moving image is the webcam image, because we really don't want to distort the IR image. We've got temperature values at each pixel. We really want to keep that intact. So we're going to warp the webcam image onto the thermal image. So let's go ahead and run this section. And here we have the tool, and what happened, I'm going to zoom these out so you can see them a little better. And essentially it's just simply like connecting the dots. I'm going to look at this, pick a point here, for example, this bottom left-hand corner of the semiconductor chip here. I'm going to pick the corresponding location in the thermal image right here. I'm going to pick maybe the corner of this USB connector right here. I'm going to do the same in the thermal image. And so you keep going back and forth. Here you can see it's going to try to predict where the other point is. So if I click here, let's see in the corner of this power adapter right here, it's going to pick the corresponding, and it's actually pretty accurate. Let's pick the bottom half of it right there, and you're just going to pick several points going back and forth, and these points are going to essentially tell the algorithm how to scale and map again the webcam image and warp it onto the thermal image. So once you're done there, I'm going to export the points, and here we have the moving points and the fixed points on into our workspace. And here's the workspace. If you look here in MATLAB, this is where all our variables are stored. So you can see our infrared image, our webcam images. Here's the fixed points and the moving points. Now we're going to do what's called a transformation. So we're going to use a function called fitGeotrans, and you can either hit F1 or right click and go here for help. And essentially this is going to fit or make a geometric transform using the control point pairs. So we're going to go ahead and run this function. And all that it was doing here was saving them as mat files. So these are essentially files that you can keep in the workspace. Say I want to reuse these control points over and over again. So as long as I don't change the orientation of my cameras, I could use these same points that I gathered for this session in maybe a future use. So going to this last section of code, this is where we're going to take, and by the way, the output of that fitGeotrans is this transformation matrix. Once we have that, this last section here, we're going to look at the infrared image and do an IMREF 2D. So what that function is essentially is mapping to real world coordinates. So once we have this, we'll then be able to do a warping. We're going to warp the webcam image onto the thermal image. So let's go ahead and run this. And you'll see here, we've actually done a really good job. You can see the thermal image here. We've essentially fitted or warped the webcam image onto it. So now we've actually have sensor fusion and we've registered the two images. And now just to move to a streaming example, because this was just taking a single snapshot of both, I have this little for loop here where I'm going to do about 2,000 loops and essentially grab a snapshot from the webcam as well as my FLIR camera. I'm going to do some contrast adjustment and essentially do warping over and over again. So let's go ahead and run this. And now you see I have live registration, or what we have here is sensor fusion. So that's all there is to it. So Dave, you mentioned that you actually want to detect and track things in the thermal space. Is that correct?
That is correct. We have customers many times who want to take a region of interest, and that region of interest may be in motion, or the camera may be moving, yet they still want to be able to track it and maybe even extract thermal information from that region of interest.
That's great, because what I'm going to show you now is we definitely have detection and tracking capabilities with MATLAB. And here you can see in these images here is that, it's easy in the case that if you have a moving, here's a bouncing golf ball, we can easily segment it and isolate it from the background. But more importantly right here, we're able to track and detect it. So as you can see here, the little X's and O's, that actually tells the zeros are where the predicted movement is and the X is where the actual. So definitely it's like your thermal images can easily be detected and tracked. So let's go ahead and get into MATLAB and I'll show you quickly how we did this. To perform object detection and tracking on thermal images, what you're going to do is go to one of our standard examples from the Computer Vision System Toolbox. So if you just type Vision Demos, so this will go to our examples for Computer Vision System Toolbox. And if you scroll down, you'll see the motion-based multiple object tracking example. If you click here we get a nice description as well as code snippets and nice images of what the demo is actually about. You can actually open the example in MATLAB. I already have it open. Let's go ahead and browse the code. You get a lot of comments, again, describing what's going on. In the beginning, there's a lot of initialization. For example, here we're setting up the video file reader as well as the player. If you scroll down some more, this is where the meat of the algorithm begins. Here we have the foreground detector. So this function in the toolbox essentially separates the background from the foreground purely through movement. So the golf ball is moving, so it's going to separate that from the background and isolate it. And then we're going to do some blob analysis. And what we're going to do here is set a threshold of 20. So this blob analysis with a threshold of 20 will say anything that's 20 pixels in mass or larger will be detected and tracked. Other than that, it will filter it out. So this is a pretty low threshold. We're pretty much looking for anything moving. And if you go down a little further, we're setting up the tracks here. Here is where we do some filtering. So we're going to do some morphological operators. This is shape-based filtering to clean up, remove the noise. We scroll down some more. You're going to see right here, this is where we're setting up the Kalman filter. So this is a very powerful algorithm. What this does is it actually predicts the trajectory. So you'll see that marked with zeros, and it corrects it with little markers we're going to use as X's. So if you scroll down here a little further, you can see we're going to mark these little paths. Again, the 0 is the predicted path of the ball, or trajectory, and the X is the actual. And then finally, we're just going to display the results to the screen. All right, so let's go ahead and run this example. Here we're going to do multi-object tracking on a video of the bouncing ball. And there it's loading it up. And quickly on the right hand side here you see the foreground detector separating the ball, doing filtering. But more importantly, on the left hand side here you can see the golf balls being tracked. We've got the zeros for predicted, X for the actual, but more importantly, look inside of the label. We're actually taking spot measurements of the temperature. So here you can see it's around bouncing between 70 degrees and 60 degrees Celsius. So that's pretty powerful. We can do spot measurements as the object is flying, and you saw it visibly, but we of course can record that as well. And even though we're tracking a single object, this framework is set up to do multiple object detection and tracking. Dave, you mentioned kind of an interesting topic, that emissivity, and so some of our viewers might not be familiar with that. Can you maybe explain why that is maybe a problem with thermal cameras?
Sure, you betcha. Emissivity essentially describes how well a material or object emits or reflects infrared radiation. A target with an emissivity value of 1 means that the radiation coming from that target is 100% emitted. Those type of objects or materials are called black bodies. They're very rare. Most are gray bodies, as we call them, which means they have an emissivity less than 1. So there's a certain percentage of reflected energy and emitted energy coming from that target. So for example, just real simply, let's say we have an object or material that has an emissivity value of 0.75. That tells me I have 75% emitted radiation, but 25% reflected. Now sometimes the cameras on their own, they can't tell the difference between reflected or emitted radiation. We have to tell the camera or the software, or we have to do some type of correction to essentially remove that reflected energy. And the reason why we want to remove it is so that we can accurately measure the actual temperature. And that reflected temperature can sometimes interfere. So that's where emissivity correction or accounting for emissivity becomes critical.
Got it. Oh, it makes sense. So yeah, so you're like we talked about earlier, because I can see my reflection in the glass per se, that the camera is actually picking that up and actually adding to the, I guess, apparent temperature, which is incorrect, and we'd like to subtract that out.
That's right. The cameras see apparent temperatures.
Yeah.
And then there, of course, is the actual temperature, which is the real temperature of our target. Our goal, our objective is always to try to equate the two.
Exactly.
And sometimes we do that through the correction process.
That's great. And it's one thing's nice is, again, coming back to matrices and the way MATLAB can connect directly with the cameras is we can actually easily take care of that. So now let's go ahead and get to MATLAB, and I'll show you how we can actually calibrate it and essentially get with this corrected, what we call an emissivity map, and essentially apply it to all future images, essentially subtracting out any additional noise or reflections that could be throwing off your measurements.
Yeah, and what you're describing, Andy, is so powerful. It goes beyond what we can do in the Research IR software, which is the off-the-shelf, let's get started, let's run quickly. In Research IR, we can do emissivity correction per ROI. The power is what in what you're describing is doing it at the matrix level now and doing it pixel by pixel.
Correct.
That's amazing.
Yeah, and so let's go ahead and get to MATLAB, and I'll show you how we do this by taking some sample images at different temperatures. Doing emissivity correction in MATLAB is actually quite straightforward. Here I already have my script open, and as you see here in this section of code, I have the first, as far as image, I took a thermal temperature at 15 degrees C. Here I have the temperature set, temperature 1 at 15. Here's my second image taken at 25 degrees C. I set the reference temperature, and here's a simple equation. So here we have, to get the emissivity map, I subtract one temperature from the other one and also do the absolutes, and I'm just saving them to the workspace. I calculate the radiance here as well, and then finally I'm able to now apply the emissivity map to a new image that I have, and this is one that's captured, and I can do the essential correction. And so this is all the code that's necessary essentially to do emissivity correction inside of MATLAB. And because we have direct connections through things like gigabit vision or USB, we can directly connect to the camera and correct for it on live images that could be coming in, because we can apply the correct emissivity map and the proper radiance maps to any future images. A last topic is actually how I think MATLAB can help some of your customers is something called camera calibration. So I'm not sure, correct me if I'm wrong, but do you ever deal with lens distortion issues? Maybe you have to put different filters and different lenses to get wider fields of view, and as a result, does it like distort the image?
We do have those situations on some of the cameras when we go to wide-angle lenses, and most definitely we're using filters in some of these cameras as well. That can change our field of views, and it can create some distortion. So this is definitely something we could use.
Good, I'm glad you said that. Because in this next section, we're going to show how we're going to use a camera calibrator tool that's from our computer vision system toolbox. And as you see from the slide here, what it does is, just by going through several steps, is it's going to be able to extract the intrinsic parameters. So these are parameters that are related to the internals of the camera. For example, focal length, optical centers, lens distortion coefficients, pixel scaling factors. So these are all the things that kind of describe the relationship of the lens to the sensor. And also, by going through this process, we're going to extract the extrinsic parameters. This is essentially how to find out where the camera is in location of space to where the actual fixed object is. So it's actually interesting. Once you get that, one, we'll be able to correct for lens distortion, but two, we'll also be able to measure things visually. So anything we see, we can get it down as accurate to the millimeter of how the size of maybe a heated area. All right, so let's go ahead and cut to MATLAB, and I'll show you really quickly this process at a high level. In order to calibrate a camera, what you're going to want to do is open our Camera Calibrator app. And there are two ways of doing that. You can go to our Apps tab here, where we have a number of different apps to help you do things. In our case, we want to do the Camera Calibrator. So you can click here or simply type it at the command line. So Camera Calibrator, and just return. And here we have the nice app. So this is a nice user interface, and we're going to add images. So what you're going to want to do camera calibration is take a series of pictures of checkerboards. So we actually provide one from our computer vision system toolbox examples, but you can make one yourself, and we're going to want to import these in. And before they get imported, you're going to want to select the size of the checkerboard squares on each edge. So here it's 25 millimeters. Let's go ahead and click OK. So now it's detecting the checkerboards, and you can see here we processed 23 images, we added 16, and we rejected 7. And here are the rejected ones. So for whatever reason the algorithm didn't like it. You can see in some cases it's very clear why. You want the checkerboard to be taking up a pretty good size of the screen. Here you see it's very small. Another one, it's a poor angle. It's not able to recognize the intersections. So let's go ahead and close that, but you can see we've successfully imported in 16. So you're going to want to do successfully about 10 to 12. So I think we have plenty to do our calibration. And what's nice here, now you'll see the detected points. So the algorithm figured out where the intersections are of the squares. The little yellow rectangle or square here is where the checkerboard origin is, and you can see all the different orientations. So you just again want to take images in a number of different orientations. And also one thing to keep in mind too is you're going to want to keep it at 1x zoom. You do not want any zoom taking place. You want to be taking it at the actual resolution. In our case it's 320 by 240, because if you do any sort of resizing, it will actually interfere with the algorithm. So let's go ahead and calibrate, and before I do so, you can see we have some parameters. You can select the radial distortion coefficients. With standard is 2, or the default. You can go to 3, but this is really for only wide field of view cameras. You can select skew as well. This is in our case assuming that the x and y are perpendicular to one another, so there is no skew in our case, and we're not going to select tangential distortion. This happens if the axes between the lens and the sensor are not perpendicular. In our case, we're assuming they are. So let's go ahead and calibrate. And once you've completed the calibration, you'll see now we have these nice little red reprojections. So the algorithm essentially, based on the calibration, is trying to reproject where the intersections are. And you can click through them, you can see all the reprojections, but more importantly, on the right hand side here are the reprojection errors. What you want to see is a pretty close clustering here, not a large deviation. This is the line here. You You can see we have an outlier here and there. So what you can do is click on it and you can actually reject it and remove it from the calculations. In our case, it's fine. We're going to go ahead and keep it. And let's go to the intrinsic. So remember this is figuring out where your camera is in space in relationship maybe to your target. And here is essentially, if it was redrawing one stationary camera, here's the different positions of the checkerboard patterns. You can actually click this view to get a pattern-centric view. This is assuming that if the pattern was stationary, where would the camera be in space? So this is a really nice way. They're pretty helpful to show maybe I might need to show or take some pictures and some more orientations to fill things out, maybe provide more accuracy. But I think we have a pretty good distribution here. Our reprojection errors are pretty low, and also here's our image. The last thing I want to show you is you can actually undistort. In our case, we don't have a lens, but say you had a lens that had a pretty wide field of view, almost fisheye, it could be bowing the edges. You could click undistort and it will essentially straighten the edges out. So this is a pretty nice thing to correct for any sort of very wide angle lenses. And then finally, you can export the camera parameters. So by clicking on this, you can export the parameters to be used in the future in a MATLAB session. Maybe you want to correct the lens distortion, or you can generate the entire script to do the calibration over again, and you don't have to use this user interface. But to show you what you can do once you've calibrated a camera, I have this nice little script, and I'm going to go ahead and run it. For the sake of time, I'll speed things up. But what I'm doing here is I'm actually importing in an image. I have put a little black lens cap next to the checkerboard. What I'm going to do then is segment it out using some image processing, and then I'm going to detect it, and finally I'm going to measure the actual diameter of that lens cap. Well, let's go ahead and run this. Okay, and as you see here are the different pictures. I've calibrated the camera again. Here we have our input image right here. You can see the little lens cap there. Here we've segmented out the lens cap. There it is. And then here we've highlighted it and drew a bounding box around it and labeled it. And then finally, down here in the command window, you can see we extracted the diameter. So just visually, we were able to say and recognize that it's 35.48 millimeters. So this is really great. I didn't have to do any manual measurements, and you can now integrate this type of technique maybe into an automated script that you might be looking at many different objects, trying to get the sizes of maybe thermal characteristics. So very powerful once you've calibrated the camera. So you saw in the past couple demos that we showed how MATLAB can connect to the FLIR cameras, and we did quite a few things, from sensor fusion to object detection and tracking. We did emissivity correction, and as well as camera calibration. So just wanted to say thanks for the time, but also in closing, remember we had a little bit of a surprise for you. So Dave, do you want to talk a little bit about what we've been working on?
Yeah, no, this really brings it full circle, Andy. What the engineers at MathWorks and FLIR have done is they've teamed up together, and we've made compatibility for MATLAB directly in Research IR software. And what we're showing here is we are in the Research IR environment, and we have a filter option for MATLAB. And when we access that, now we can utilize MATLAB scripts within the Research IR environment. So this is huge. So for customers who are already very accustomed to Research IR but want just that little extra functionality, they can access the MATLAB scripts now directly in Research IR.
Yeah, that is really great. So it really helps, MATLAB helps to extend your environment quite a bit more. And for example, you can have different team members work more cohesively together. People who are more accustomed in MATLAB can actually be doing development there with your cameras, and also can essentially give scripts to people who are more accustomed with Research IR so they can be more productive and really take advantage of all the processing in MATLAB in your environment.
Yes, what I see this does for both of our customers is it increases their flexibility of thermal and also of doing the analysis and processing. They can do it in Research IR, you can do it directly in MATLAB, or you can do it in both.
That's great. All right, so we're wrapping up here. We're at the end of our webinar. Just like to say thank you for the time.